post-tidal disruption.
Yes, thank you. This will be a different talk, not about rates, but about one special event which I will try to simulate. And there will be no introduction, but there will be a bit of an introduction to the method which I actually use. And let me immediately jump into it. And the method combines the SPH approach with grid-based general relativistic MHD code. I am not an expert on SPH. I guess most of you know much more about the SPH approach than I do, so there is only one slide about the SPH approach. The bottom line is this is the code developed, a kind of a standard code developed initially by Stefan Roswog, which includes, however, exact accelerations acting on test particles in Kerr spacetimes. So it is supposed to it is supposed to follow the geodesics properly in the relativistic regime as well. And the idea of this project is to combine the SPH output with a follow-up simulation within the scheme of a general relativistic magnetohydrodynamics. And this is the part which I am in charge in. For this project, I used the code which I developed a couple of years ago. It is called Coral, and it combines the following elements. It combines the evolution of gas within ideal magnetohydrodynamics. It also is capable of solving radiative transfer under M1 approximation. It solves the equations in general relativity in a fixed spacetime and on a fixed grid. And this allows us to set the grid, the inner edge of the grid, even inside the black hole horizon, and trace the accretion rate through the horizon precisely. And the simulation can be done in a global context, so that the whole accretion disk can be simulated. And originally, I come from the field of simulating accretion flows, and recently I have been simulating super Eddington accretion flows. And this is an example of a simulation like that, which accretes at the rate of 10 times Eddington accretion rate. The left-hand side shows the evolution of the gas density, and the right-hand side the evolution of the radiation energy density, or radiation pressure if you prefer. So it was kind of natural to migrate into the field of tidal disruption events, because we know that we expect, at least initially, super Eddington accretion rates on the black holes. So let's think, what can we do with a code like this in the context of a tidal disruption event? There are limits to what we can do, and the limits come from the fact that this is a grid-based code, and grid-based codes have a limit on the time step that can be applied, which is related to the usually light crossing time through the smallest cell. So if we have a relatively small time step and we still need to do a three-dimensional simulation, it means that we can't simulate this event forever. So there is a limited duration of the simulation. There is the limit on the duration of simulation. Other limit is related to the resolution. The resolution is finite. We can't help that. And this, one has to take care that one has to be sure that the event that one wants to simulate will never become thinner than one or a couple of grid cells. And this leads us to a setup which is favorable in this case. So if we simulate an elliptical orbit and a large impact parameter, we can hope for the event to be kind of limited, or to be taking place in a limited region which can be covered by a grid-based code. And also large impact parameter usually gives us relatively thick nozzle so that it does not become excessively thin. And this is the SPH simulation that we initially simulated. We took the following parameters for the system. We chose the mass ratio 10⁶ with the stellar mass 0.1 solar masses, and we chose the eccentricity of 0.97, very large impact parameter of the order of 10, which corresponded to the pericenter radius roughly at 7 gravitational radii. And this is the evolution of the SPH particles in the simulation. You see that there is a very significant relativistic precession at the first encounter, and then the star is disrupted. It does not go to infinity. It's a bound star. All the debris is bound, so eventually all the gas will come back towards the black hole. And what we do, we take the snapshot of the SPH simulation just before the first particles come back to the black hole, and we translate it on the grid-based code. We translate it into Coral. And here you see actually the density at the equatorial plane, or at the initial stage of the Coral simulation, with the velocity streamlines showing where does gas go at the beginning of the simulation. And we wanted to perform 3 simulations, and ultimately we performed 2. So I will discuss initially in most details the purely hydrodynamical simulation. Then there will be a couple of slides about the MHD version of exactly the same simulation. And initially the idea was to perform also a radiative simulation, which can where one can follow the radiation field where the photons are generated, and actually they can leave the system, and one can calculate in principle the light curves. However, this very setup which we chose for this simulation turned out to produce such optically thick event that the whole domain was filled with optically thick gas, so there was no photosphere, and actually there was no point in actually following the radiation in the simulation. The parameters of the 2 simulations that I will describe are given here. The inner edge was inside the horizon. The outer edge was at 1000 gravitational radii, which was enough to cover the whole evolution of the gas. The resolution was moderate, and it was performed for a long time of 100,000 gravitational times, which corresponded for this setup to only 13 hours, and corresponded to 1000 orbits at ISCO. So please, so it was long in terms of gravitational time, but also in terms of physical time. And let us now go into the hydrodynamical simulation, and I will discuss 2 phases of that simulation. I will start with the self-crossing, which is expected, and is expected because the impact parameter was large, so we expect a lot of relativistic precession. I will show this type of an animation a couple of times. This is the horizontal slice through the simulation, so through the equatorial plane. And we see the initial input coming from the SPH simulation, and the black hole is at the center, and the gas will start falling from the top right down to the black hole. The bottom panel will show the vertical slice across this dashed line. And here is the history of the accretion rate, and this dashed line, this horizontal line corresponds to 10,000 Eddington accretion rates, and this is the accretion rate through the black hole horizon. So let us see what happens. So we see that the gas comes to the black hole. There is significant bending so that the gas comes back and hits the incoming stream. And we see a couple of things. So we see, as expected, the nozzle, and I will pay a bit of attention to the nozzle. We see the relativistic precession, and we see that this self-crossing takes place in a relatively extended region, let's say between 10 and 50 gravitational radii. And I will zoom in a moment. And there are 2 things that I want to put your attention to. One is that there is a significant quasi-spherical outflow coming out of the system, and there is also some kind of periodic pattern. But let's start with the nozzle. So this is a spherical slice through the radius 12, which corresponds to this to the region, exactly where the nozzle is located. And you see that actually the thickness of the nozzle is not small, is relatively extended, which is a good thing for a grid-based code like this. And this comes from the fact that this is a very close encounter, and also it's an elliptical encounter, which means that the distribution of the velocity vectors inside this debris is pretty wide, and actually we do not get very thin nozzle at all. This is the inner region of the self-crossing at one moment of time, where the self-crossing is kind of most evident. This is the plot showing the density, and we see that the gas comes back and hits the incoming stream between, let's say, radius 10 and 50. This is the temperature, and this is the entropy. So it is clear that there is at least one major shock where this interaction takes place, where the temperature is also the highest, and there is a trace of another shock in that region, but there is nothing in the nozzle, maybe because this nozzle is so thick. What does happen when we have such a shock? What happens is that the gas coming back carries significant kinetic energy. It hits the incoming stream, it shocks, and this kinetic energy is dissipated. And what happens is that the debris coming down towards the black hole is heated up, and the gas, which loses its kinetic energy, becomes more bound, and actually it later on falls down on the black hole. And this is once again another view of the self-crossing in the innermost region. This will be an animation showing at the evolution of density at the equatorial plane and vertical slices along the dashed line. This will show the density, this will show the Bernoulli number. So red color will correspond to unbound gas, blue color will correspond to the bound gas. And this is what happens. You see that the The gas comes back, hits the stream, it heats up the stream. The stream becomes quite hot, and then it is likely to drive some outflow. And this, we see that there is quasi-spherical outflow coming back from this region, which is heated up by the returning stream. And if I relate again, we also can notice that there is some kind of periodic behavior. So we see like waves of gas leaving out the system. Let's pay more attention, let's look closely at the outflow and the gas flowing out from the system. So let's define a sphere of a radius 100, and let's integrate the accretion rate. Let's integrate the amount of gas crossing the surface and plot it as a function of time. This is this purple line on this plot. And then we can do exactly the same exercise at the outer edge of the box, and this would be the orange line. So we see that plenty of gas is crossing the surface. It's reasonable because this gas is not limited to the gas which comes back to the black hole is deflected. It's not limited to the radius of 100. It by itself wants to go also to larger radii, but significant fraction of it is actually the gas which is flowing out through this quasi-spherical outflow. And we see some periodicity in this curve of the accretion rate. And one can also notice that the amount of the gas which crosses ultimately the boundary of the box is lower. It's roughly, let's say, third part of the gas or fourth part of the gas that crosses radius 100, which means that from the gas which flows out through this radius, through this sphere plotted here, only fourth part actually leaves the system. The remaining part will ultimately come down on the black hole because it was not unbound enough to, to leave the system. Okay. So where does this periodicity come from? It comes from the following fact. We can easily imagine the following like feedback loop. We have an accretion flow which is deflected, stream which is deflected. It hits the debris from more or less the same side from the other side, but it contributes more to the angular momentum of that. It increases a bit the angular momentum of the incoming debris, which means that if you increase the angular momentum of the debris, it means that the pericenter radius moves slightly out. If it moves slightly out, it means that the deflection angle, the relativistic precession angle will be lower, and you will start hitting the debris at larger radii, where you will less efficiently affect that debris, which means that its angular momentum will come back to the original value, and the same thing happens with the pericenter radius. And then you again start hitting the stream with large efficiency. And there is this kind of feedback loop which drives the type of oscillations printed on top of the amount of gas flowing out of the system. In this very simulation, the period is 800 dynamical times, which corresponds gravitational times, which corresponds to the Keplerian period at radius 25, which is more or less where the self-crossing takes place. So if one writes down the formula for the Keplerian velocity or Keplerian angular velocity as a function of radius and as a function of black hole mass, one gets the following number. So for typical parameters of a tidal disruption, one should expect the period of that roughly at 10 to minus 3 hertz, so like 1 hour. Okay, and such a periodicity will be visible or efficient only in case of a close encounter, where this kinetic velocity of the precessed flow is significant when compared to the energy in the incoming stream. But it also requires zero black hole spin, or at least if the black hole spin is not zero, that the plane of the incoming star is actually coincides with the plane of the black hole spin. So there are some conditions that have to be satisfied, but it is possible, and this is what we see in the simulation itself. So the summary of the phase 1 is that we see outflows, that we see some periodicity, and actually the accretion rate, which falls on the black hole, and this is marked with this red dashed line, is significant in terms of the Eddington accretion rate, but it's not so significant in terms of the total amount of mass available, and it comes from the direct accretion resulting from the self-interaction of the debris. Okay, now the second phase. The second phase is the phase where the disk is formed, and this is now we continue the very same animation, and we see that the star comes down, and after a couple of hours, it is actually all the debris of the star is within this box where I plot this animation, and you see that actually the disk circle arises pretty quickly and forms a beautiful disk-like structure, which is very optically thick and which is turbulent. So what happens? The circularization takes place once all the debris is down in the inner region. And why is this circularization possible at all? We originally have angular momentum and specific energy corresponding to an elliptical orbit, but we end up with a circular orbit at much smaller radius. How is this possible? To obtain a circular orbit at a lower radius, we need to get rid of the orbital energy. And this actually happens. The orbital energy is of the gas is going down and approaches more or less the Keplerian value, and this energy goes both into driving the outflow, which we have just discussed, but also it goes in a significant fraction of it goes into the thermal energy of this flow, and the flow becomes so hot that, as you will see in a moment, the gradient of pressure can actually support this structure. And then we have the average structure of the circularis disk, a beautiful polished, very thick polished donut. Let's look at the properties of that system. The angular momentum is very low, and is more or less corresponds more or less to the angular momentum of the initial star, and is much lower than in case of a regular super Eddington accretion disk I like to simulate. The specific energy of the disk, it is also more or less, the total specific energy is more or less equal to the stellar specific energy, but if we plot only the orbital energy of that gas, it is more or less Keplerian, and the excess goes into the thermal energy. So what is this like? What is this disk structure like? It's weakly bound gas, it's low angular momentum, it's more or less like zebra, like predicted. However, it's not exactly zebra because it has like constant angular momentum, which was not exactly taken into account in that model. But it is more or less exactly thick zebra as expected. Now the history of the accretion rate. On the black hole, this looks like that. The initial phase comes from the direct outflow, and where does the late stage come from? The late stage where do we get the accretion after the circularization takes place? This is a plot which shows the local accretion rate on the poloidal plane, and somewhat surprisingly, the accretion does not take place in the bulk of the disk as usually in accretion disk. What happens is that most of the accretion comes actually along the edge of the torus. The gas actually falls down on the black hole along the polar axis. Where does it come from? It comes from the fallback. So you remember at the initial self-crossing stage, we had plenty of outflow coming from the system. At the late stage, we have plenty of inflow coming roughly along the vertical direction. And the turbulence that we see inside the disk, the hydrodynamical turbulence, is not efficient. It is not producing significant accretion near the equatorial plane. So the summary of the phase 2, we have circularization, we have zebras, but the accretion comes through the fallback, only through the fallback. Now we go to the MHD simulation, exactly the same initial setup, but I put some very relatively weak magnetic field in the initial star, and this magnetic field is brought in with the gas towards the black hole, and then yes.
It's in the star in the SPH.
No. Just after translating onto coral, I put some arbitrary magnetic field at the initial stage of the grid-based simulation. It was not in the SPH. And this magnetic field is initially insignificant, but we have differential rotation, and differential rotation means that the magnetic field lines are stretched and they grow in power. And this plot shows that the colors, which are on top of the original density plot, shows the ratio of the magnetic energy density to the rest mass energy density, and you see that with time it goes up, increases in power, and also extends to the larger radii. If it was like a regular standard disk, we would expect that this grows up. At some point, the resolution is enough to resolve the magnetorotational instability, and we end up with a typical like accreting system. However, this is not the case here. This shows the ratio of the magnetic to the gas pressure as a function of time, shown with different colors, and as a function of the radius. And we see that the power of the magnetic field grows with time, extends to larger radii, but it saturates. And it does not saturate at the level of where we would expect it. For regular disk, it would be 10 to minus 1 of the total pressure. Even if our resolution was very poor, and we could not resolve magnetorotational instability, we should expect that the magnetic power would grow more or less to the equilibrium stage, to the equipartition state. This does not happen here. Magnetic field saturates at very weak level, a very low level. How is this possible? These are the particle orbits in a standard accretion disk. 10 times accretion rate, 10 times Eddington accretion rate. I put crosses in 4 points along the radius 100, and I trace the particles for more or less 1 orbital period at that radius, and this is what we get. Beautiful circular accretion. But remember, the disk which I get here has a very low angular momentum, actually almost flat angular momentum, which means that the particles go much slower along their orbits, along the azimuthal directions. These are the trajectories of the particles in the tidal disruption disk. They are completely different, and this comes from 2 facts. One fact is that they are very slow in their azimuthal motion. The second fact is that they are very energetic. They are almost exactly marginally bound. So there is plenty of power which can kind of steer this gas in the poloidal plane, and it makes the particles go to the left and right. James.
Well, like you go to the previous plot. So the magnetization tends to be higher to go closer to the black hole.
Yes.
That's the general trend. So for a less extreme disruption, say beta is 1, would you expect the trend to basically start out at this level and go even higher as you go closer to the black hole, since the orbits will be getting more circular as you go closer in?
I do not have a good answer right now. I will have to think about it. Let's talk about it. But it does grow to larger numbers when you get closer to the black hole, because you have more orbits that you can cover within a given physical time. But as you see that actually even in the innermost region, you saturate the number. So it seems like you saturate at some level, and it should not grow up longer. So the idea is that here we do not have a good, well-defined, well-pronounced differential rotation. What we have is rather gas, kind of turbulent gas with not so significant azimuthal rotation. Okay, so this is the summary of the magnetization thing. It does saturate inefficiently at the level of, let's say, roughly 100 times weaker than standard accretion disk. In this simulation which I performed, this level was not enough to resolve magnetorotational instability, so I don't see it. But if my resolution was infinite, I would still expect that the MRIs would saturate at a level much lower than in standard accretion disks. So let's say my guess is alpha would be 10 to minus 4. What does it mean? We move gas close to the black hole, we generate this Polish donut torus, or that zebra torus, and we put in viscosity 10 to minus 4. What accretion rate we get? We get 100 times lower accretion rate than we would got for typical viscosity 10 to minus 2. So this may suggest that the accretion rates that we ultimately get from the circularized disk will be very low. The bottom line or the takeaway point from the MHD simulation is viscosity is probably inefficient. The summary slide. So I performed a simulation Hydro and MHD of a close encounter with elliptical orbit. Initial state comes from SPH simulation. We resolve horizon, and what we find is definitely not the standard picture. We have outflows, we have periodicity, we have direct accretion initially, but later on we have weakly bound torus of gas, and the accretion only from the feedback. There's no direct accretion in the equatorial plane, and if MHD and the results from the MHD part suggests that ultimately the viscosity which will be triggered in such a system will be inefficient and will not bring enough magnetic field to generate jets, and will produce very low accretion rate through the black hole. Thank you. I will appreciate questions.
I'm going to take the chairman's privilege.
Yes.
And
yes.
I want to understand your argument about the no MRI, even though you don't actually calculate it, which is the claim that the orbital shear is very low?
Yes. It's difficult to define only shear, because there's shear, like typical shear would be in the azimuthal direction, and we have also a lot of shear in the radial direction because of this turbulent motion. So shear will be different. This is what I would say, and my guess is that it would produce less efficient saturation level of MRI.
You can quantify that.
No.
You can quantify the actual shear. You can measure it in your data.
Yes, but well, okay, I can quantify azimuthal shear, I can quantify radial shear, but it will not tell me how efficient, at what level the MRI would saturate. One would have to study this like kind of independently.
You need to actually calculate it to do that, but you can at least you can normalize that shear in units of the local orbital frequency, and characteristically the growth rate is proportional to that shear.
Yes, but this is not clear to me that if the radial shear will be comparable in power to the azimuthal shear, then we can kind of directly extrapolate or take standard MRI picture to this regime.
Yeah, that may or may
I think it matters because we have this significant radial motion, which significantly affects the saturation level of the non-MRI magnetic field. So it seems natural to expect that it will also affect the saturation level of the instability. Excuse me?
Natural is subjective.
Okay, yes, absolutely it is.
Okay.
I have two quick questions about outflow. The first is, where is it being launched from? In the simulations, I saw some material coming out of the nozzle, but maybe other coming out of the self-intersection point. The second question has to do with the ejection velocity of the outflow, which seems to be not related to full outflow, which is bound. But that seems to me to suggest that there's some fine-tuning process going on, because you're tossing the matter out from 10 RG, it's making it out to hundreds of RG and then turning around. If you were putting in 10% more specific energy, it would be totally unbalanced. So what's the idea?
Okay, so first thing is that it is launched from that region of the self-intersection, but mostly from the layer where the two streams interact with each other. There is a continuous spectrum of the energy of the ejected outflow, so it's like some of it goes to 100, but some of it goes to 500, some of it goes to 550 radii. And maybe one point that one should make is that this was a bound orbit of the star, right, which is relatively bound, and the debris is bound at the level of 2 times 10 to minus 3. If we had a parabolic orbit, it would be probably 10 to minus 4, 10 to minus 5. Then one should expect even more outflow if the pericenter is so close and if the shock effect is so important.
So this calculation does not include any effects of radiation pressure, is that correct?
So it did not. However, if you kind of mimic the radiation pressure by the total pressure of the gas. So if I performed exactly the same simulation with radiation, and it is totally optically thick, so it would look exactly the same, but my temperature of the gas would go down from 10 to 11 to 10 to probably 7, and the rest of the pressure would be provided by radiation.
What was your adiabatic index?
If 4 over 3. So it's like optically thick, but the adiabatic index would probably not be too important.
About this self-crossing, this would imply shocks.
Yes.
And I didn't spot exactly what are the typical temperature which are produced at these shocks.
Okay, this is the plot. The red is 10 to 11. Okay, so this is kind of orange, so 10 to 11. But once again, this is purely hydro, and that's the point which Nathaniel made. If radiation pressure was included, probably the gas temperature would go down.
So this periodicity that we see, it says like 1,000 second times or something like that.
Yes.
So in the Swift A1644 X-ray light, variability of those times.
Which is like natural time scale, right, for a supermassive black hole. But that may be one possibility. So how this periodicity is imprinted on the light curve is kind of an open question. In this very simulation, it is kinetic energy of the outflow. But if it was less optically thick, so then I would suspect that, well, definitely we have this periodicity with in the amount of power which is generated at the shock. And if the cooling time there is short and optical depth is low, this would immediately be imprinted on the radiation. But if it is X-rays, then it is in the jet. So that makes it more complicated. I don't know how to explain that.
And then you probably have an orbital plane tilted to the spin axis.
Yeah, this is what I pointed out. Zero spin, you get it. With non-zero spin, it's more difficult.
Yeah, I just had a quick question about your argument that the outflows are partly responsible for depriving you of the energy which you need to do for circulation. The outflows are bound; they're not taking away significant.
Well, but they are less bound than the original gas which falls in. So they can take some part of the energy.
Sure, but I think it's going to be a very small part of the energy.
But in your simulation, it goes out the outer boundary and never returns, doesn't it?
So third part of the outflow goes through the outer boundary. Yes, and never returns.
So in effect, that does take energy from the system.
Okay, so it takes energy from the computational box, absolutely. But if speaking in terms of the energy taken away from the innermost region, then, well, they do, simply. They do take the energy.
Comes back,
Exactly.
conserves, unless it cools on the outside.
Well, total energy is conserved. I'm just
Right, that's what I say. And unless it can, suppose you had a box that went out to infinity.
yes.
Then if the streams are found and they don't radiate, then energy is conserved and it comes back. It may change form, but it comes back.
Yes, but
So
what's
the
the
only way you can conclude is if they radiate from at a large distance, the optical depth is smaller.
I'm lost the point. So what's the point?
Oh, yeah, but the energy doesn't actually leave the system.
Yes. Okay. Yes. Absolutely. The point is that the gas of the star is bound, and by itself it would not go out further out than, let's say, to 500 gravitational radii. This is the orbital energy of the star, but it goes further out, so it had to get energy from somewhere. And
Sure, but the difference in 1 over 500 RG and 1 over 5,000 RG is tiny relative to
you're making a good point.
Energy, which is what you need to circularize as energy, right? So that change is not going to be.
You're making a good point. So what I will do, I will quantify the amount of energy taken by the outflow and compare it to the energy deposited in the thermal energy, and probably I will find that it is not so significant. Good point.
Yeah, I just wonder how this kind of disruption would look like because of these enormous temperature, and I guess the densities are also very high.
The density of the gas?
Yeah.
These units are screwed up. 10 to minus 4 grams per centimeter cubed. Mm-hmm.
So the electron ion coupling.
Well, but I think this particular setup would be optically thick, so they would be coupled efficiently.
Yeah, then you have basically a GRB.
It's not yet that level, I think. It's 10 to 4 Eddington accretion rate. It's not yet in the regime of gamma ray bursts.
Disruption, these very thick tones, which is high
Yes.
pressure.
It approaches this regime, I do agree. And maybe one remark I should have made in the beginning. This particular setup, which is simulated, is super unlikely. I chose it because it's convenient from the computational point of view. But I think that after every step, one can make this mental experiment and think what it would look like for a parabolic encounter. In most cases, one can say that it would hold for parabolic encounter as well, as long as the impact parameter is very large.
So are you resolving, you think, the spiral shock that you see in your simulation? You can get a lot of magnetic field amplification.
Which is the spiral shock?
So that red spiral shaped thing in your temperature
Here?
diagram. Yeah. You think that you're resolving that well?
I would have to do the numbers. The resolution in the radio, the grid size in radius is logarithmic. So actually, like half of all my cells are actually in this region. So I would not be worried about the innermost region. The resolution is pretty high over there. But let's do the numbers together.